Good day, I'm Dr. T and welcome to my office. So today I'd like to talk about our understanding of the makeup of matter. The way we understand matter working has evolved throughout history. The Greeks had quite a few very interesting ideas, and I'll just leave it at very interesting. Our modern understanding, though, ends up becoming more of a thing in the beginning of the 19th century with the assistance of an individual by the name of John Dalton. Dalton's idea later became what we would now know as the billiard ball model of the atom. Billiards is a game similar to pool. So, pool balls for atoms. And in this idea, we have atoms that are small, hard spheres. They can't be created or destroyed, and they don't change from one to another. Those substances that are known as elements are going to be made entirely of one type of atom. And that type of atom is that element. Those substances that are known as compounds, these are substances that can be broken down into constituent elements, whereas elements cannot be broken down. Compounds can be broken down into constituent elements because they are made up of two or more different types of atoms, which in chemical reactions can either be rearranged or separated into their own groups. Now, understanding matter in this way is actually incredibly useful, and in many respects, one of the most common ways of doing so within chemistry, even to this day. However, it's definitely an incomplete understanding of chemistry because, hey, the atom is made up of stuff, and that stuff can matter. So diving into the atom is a task that we started undertaking in the late 19th and early 20th century. It actually wasn't until the 1930s in which we actually understood the full makeup of the atom. So atoms contain within them three different types of subatomic particles. The first subatomic particle is the proton. This is positively charged and has a fairly meaningful amount of mass. This is located within the nucleus. The nucleus is very small and is typically best described as a tiny speck within the center of the atom, but despite its diminutive size, contains virtually all of the mass of the atom. The electrons, which are not in the nucleus, do have mass, but not much. So the number of protons within the nucleus determines what type of element that particular atom is. Neutrons are also going to be existing inside the nucleus. They don't have a charge and typically help stabilize the nucleus. Now we can start describing the nature of this nucleus with our atomic symbol. So atomic symbol is going to start out with the 1 or 2 letter abbreviation for the element in question. Now, this may be 1 or 2 letter abbreviation for a language that's not English, so be forewarned. Latin is popular. The number of protons, which is also known as the atomic number, can be placed on the symbol in the lower left-hand corner. This is actually not done very often since this is redundant with the symbol. If I have, say, helium, I know that there are 2 protons because it's helium. And if I have 2 protons, I know it's helium because there's 2 protons. So this number is quite often omitted, but can be present. In the upper left-hand corner is the atomic mass number. This is the sum of protons and neutrons, both of which have roughly the same mass and comprise the vast majority of mass of the atom. Now, because the neutron has a neutral charge, it doesn't actually impact the chemistry of the atom very much. And so atoms with different numbers of neutrons will have very similar chemistries, although the change in mass can affect the chemistry, so they won't have exactly identical chemistry, but it will be very close. These are known as isotopes. Iso, same, tope, substance. Now, the third constituent of the atom is the electron. The electrons are buzzing around the nucleus, and I use the non-technical term buzzing because the electron's behavior is actually really complicated that I will barely touch on in later videos, but in general try and avoid. This is where quantum physics becomes a thing, and quantum physics is not fun. So, the electrons are buzzing around the nucleus and take up most of the volume of the atom. When we talk about the volume or the size of the atom, we are really talking about how far out the electrons are buzzing around the nucleus. Electrons are negatively charged. Their charge is equal and opposite to that of the proton. Because of this, if there's the same number of electrons and protons, then the charges will cancel out. This is what we call an atom. If, however, there is a difference in number of electrons to protons, then the charges will not cancel out. There will be a net charge, and this is what we call an ion. The charge of an ion is the protons minus electrons, and is written in the upper right-hand corner of the atomic symbol. Unlike the number of protons, the number of electrons can readily be changed during a chemical reaction, so an atom can convert into an ion or back, or from one ion to another fairly readily, depending on the chemical reaction that's being involved, although any change in the charge will involve a chemical reaction. The last remaining corner of my atomic symbol, the lower right-hand corner, is reserved for the number of that particular ion or atom inside of my compound, and we'll talk more about that in later videos. With that said, have a wonderful day, and I'll see you later.